Hello, everyone. Welcome to the latest episode of Unwind. Glad you all could join us here. For those who aren't familiar, Unwind is the Handmade Network's live Twitch show where we interview members of the handmade community about their work and their projects. And this is our May episode, although this is being recorded on the 1st of June. We are very pleased to have Martin Fouilleul with us today. Martin is if you're a member of the handmade community, I'm sure Martin is a familiar face already. Martin is the project lead for Orca, which is an exciting new platform for developing cross-platform applications in WebAssembly. And I knew there was going to be one step I forgot with this whole AV thing. My apologies. Let's see here. Oh no. Martin, what did I say that I was going to do at the start of this? I needed to switch off the I don't need the Discord audio, whatever that is. I've got my mic. I've got your, can you say a few words here? Need to make sure that we can.
Hello. Hey, hi, 1 2 1 2. Do you hear me?
I do hear the echo on you as well, actually. That's odd.
Oh, that's bad.
We did all the AV testing right before this.
Yeah.
Of course. Okay, so is it because I'm hearing you in, where am I hearing you now? Oh no. Yeah, I need to turn off your audio in video somehow. I don't remember how I turned it on in the first place. So, tell you what, 1 second, sorry. We're gonna be right back. All right. Is that any better? Was this the problem? Do I have it fixed now?
Hey, 1 2. We're back.
Sounds good to me now. I forgot that I had done the audio monitoring thing in video. And
cool.
Hopefully now it sounds good on my end. Sounds good. I see bouncing audio meters in OBS now. All right. First time using this new screen sharing and video control program for all of our AV, so apologies for that. Anyway, maybe I should start my intro over so some future edit of this can be a little bit better. But hey, welcome to Unwind. This is our show for the Handmade Network, where we interview members of the handmade community and they get to present about their projects and their research or anything else that they're working on. Today we're joined by Martin Fouilleul, who's the lead of the Orca project, which is this really exciting new platform for cross-platform app development. It uses WebAssembly and a lot of other really interesting tech, and Martin's going to be talking a bit about the vector graphics component of that today. So Martin, welcome to the show.
Hey Ben, thanks for having me.
So I've been excited about Orca for quite a while. It's the kind of idea that we've had brewing within the handmade community for a really long time. I'm sure you'd agree. And now, because you took the initiative to get this thing going through a jam project that you did for, was it last year's wheel? It was the year before, the two-wheel reinvention jams ago, yeah. Thanks to that, then that kicked off this whole project, and now, not only have you been able to get a pretty substantial version of Orca out into the wild, although still kind of early alpha. I've even got, like, back here in my office, like the oops, how do I show it on camera? The CI machine for Orca sitting right there, so we can do all of our Mac development things and variety of platforms. So Orca is a fun project, and I'm glad to have you on the show because the vector graphics component of Orca is both really interesting and also, I think, kind of unique for the handmade community. There's a lot of like 3D graphics types in the community, but vector graphics is not something that's touched very much. So what sort of got you interested in that before we get into the actual presentation about it?
Well, I kind go into that in the presentation. But
okay, well then I won't.
Maybe I just say a word about that when starting.
Yeah, fine. I won't beat around the bush any longer. Let's cut over to your presentation here. I'm actually not seeing your slides yet if you want to get those up.
Can you see that?
Yep, I will transition now. So, without further ado, let's hear Martin's presentation about vector graphics.
Hey, hello everyone. So I'll be talking about my personal journey into vector graphics. So I will be presenting 3 different techniques that I experimented with for doing vector graphics rendering. And so there are a lot of different methods and techniques to render vector graphics. This is very much an open field for research, has been for a long time. And I will only cover those methods that I personally have experience with, but that might also give you some leads and some references if you want to go from there and explore a little bit more in depth if you're interested. So let's say a word about Orca. So I do a bunch of stuff, but mainly my main project right now is working on Orca. It is, as Ben said, a platform for portable sandbox graphical applications. Basically, we take a WebAssembly module and we bundle it with our own WebAssembly runtime that platform. So for example, you can have input events, file IO, graphics, etc. You can read more about Orca on orca-app.dev. There's a number of blog posts there. But point being, in Orca, there is a vector graphics API that allows you to draw 2D stuff, and that is also used by your UI system to render the UI. So quick word about what vector graphics are. So it's a different way of computing images opposed to raster images. So instead of storing pixels for your image, basically you have the shapes of your image that are defined in terms of lines and curves. So you have paths that have like an analytical expression, and then you have operation on those paths. So you can fill a path with a color or an image or a gradient. You can stroke along a path with a given width and with some styles for the joints. And the advantage of this is that it's scalable. So since it's not tied to some size in pixels, you can scale it and avoid having artifacts of upsampling and downsampling that you have with raster images. So what got me interested in vector graphics in the first time? So once upon a time, I was working on a project called Top, which is a hierarchical cue sequencer for sounds and light effects and videos. So you can organize cue lists and trigger sound effects, for example, during a live show. This project didn't really pan out, but I learned a ton. And at the time, I was starting doing my own UI. And for drawing the UI, I was using a vector graphics library that's called Chau Graphics. At the time, it was software render. They might have added GPU backend now, but point being, it was super slow. Take that with a grain of salt, because that might also be like half the problem might have come from me, because obviously I wasn't as experienced with these things as now. So maybe Chau wasn't that slow and I was. I don't know. Point being, at that time, I told myself, well, how hard could it be to down my own vector graphics? And I could tailor that to my own needs, and I could optimize that as much as I want. And that's how you fall into rabbit holes. So the first iteration I did on that is pretty simple. You have curved paths. You just subdivide them into smaller paths that you can consider as line segments. So basically, you linearize all your path, and now you have only polygons. And for strokes, you can directly generate triangles for all the lines and joints. And for filled polygons, you have to triangulate the polygons. Then you have that triangle soup that you upload to the GPU. And you let the graphics pipeline do the rest of the work for you. So I have a series of blog posts on my personal website about that iteration that you can look up. But let's see how it works in a little bit more detail. So the first step is subdividing, like linearizing curves into like piecewise polylines. So you have curves that are generally defined as quadratics or Bezier or cubic Bezier curves, and you want to convert that to a polyline between a start and end point. So what you do is that you just evaluate the point on the curve at the middle parameter, and you check that that new point is close enough to the middle of, like, to the segments joining your start and end points. And if it's too far, you just subdivide the curve at that parameter and you recurse into each part of the curve. So you have a trade-off between how faithful you will be to your curves versus how much you have to recurse. And you have potentially pathological cases where if you have very twisty curves, you will have to recurse a lot. Then to do stroking, it's pretty simple. You can iterate through angles of your path. So you iterate from the middle of the segment to the middle of the next segment. So you always include a joint, except for like the first beginning cap and the last end cap. But generally, you just compute outward-facing normals for each half segments. So that's a bunch of cross products. You scale that by half the stroke width, and that allows you to compute the points of the outline and triangulate it directly. So that part is pretty simple. The thing that is a little bit more interesting is how you do triangulation. So let's first start with triangulating monotone polygons. And so a monotone polygon is formed by two monotonic chains, and a monotonic chain is a sequence of vertices of that polygon that goes in one direction along one axis, but like never goes back. So a monotonous polygon is made of two monotonous chains, one that goes down and one that goes up. So if this polygon is wound in counterclockwise order, you have the chain going down on the left and the chain going up on the right. This kind of polygon can be triangulated in linear time by a sweep algorithm. And what you do is that you go, so you sweep your line from top to bottom. So you go to the sorted list of vertices, and you push them on a stack as you go. And each time you consider a new vertex, you try to make triangles with the vertices that are on the stack until you can't, and you push the last 2 points on the back on the stack. So let's see how that works in action. So I'm starting at the first point on the very top. So I push that on stack. Second point, I can form a triangle because I have only 2 points, so I push that on stack. And here I try to form a triangle with points that are on stack, and I can't because my segment is going outside the polygon. And how do I know that? Basically, I have to have the correct winding for my triangle. So if I go from the red vertex on the top to the next red vertex to the green one, I see that my triangle is wound counterclockwise. And since I am on the upgoing monotonic chain, I should go on the opposite winding as the polygon. So this triangle is not good. This one is not good either. But then this one is good because it's wound in the opposite side as the polygon. So I add this triangle, and I try to go up the stack like that, creating triangles. So I can create that one, and that one is not good. So I just push the last 2 points on the stack, and I go to the next point. This point is on the opposite monotonic chain as the top of the stack. So I know that I can like pop all my stack and create triangles for all the vertices on the stack. So I do that. Then I have a new triangle here that is correctly wound, and my last triangle here. So we have triangulated a monotonic polygon, but now we want to triangulate polygons that are not necessarily monotonic. So let's categorize kinds of vertices a bit. So in a polygon that's not monotonic, you have start vertices that are basically the tips of the top branches of the polygon. You have merge vertices when two branches of the polygon merge. Regular vertices are those who have neighbor above and below, so they are just kind of polygons, points on the side of the polygon. Split vertices are those where you have a split and you have two branches on of the polygon going down. And stop vertices are the bottom corners. And you can see that merge vertices and split vertices are responsible for the non-monotonicity of this polygon. So what we want to do is create cuts inside that polygon between merge vertices or split vertices and another vertex on polygon to split or non-monotonic polygon into a monotonic polygon. So let's introduce the notion of a helper of an edge relative to a scanline, which you see on the right. So if I have an edge E in red and a scanline L, the helper of E with respect to L is the lowest vertex of the polygon, from which I can draw a line to the edge, which is entirely contained in the polygon. So then we can split simple polygons into monotone polygons with another kind of line sweep algorithm. We'll keep track of cuts in a data structure C, and we'll keep track of left edges and the helpers in a data structure S. And each edge can also have, can also remember a pending merge, which is the last helper it had, which was a merge, and which wasn't used in a cut yet. And so we sweep our line from top to bottom, and we update S and C as we encounter vertices according to the 6 rules that you have on the right, and basically according to the different kind of vertices that you encounter. So rather than going through all those 6 rules one by one, I will work through a simple example. So I have this polygon, which is not monotonic. I start at the top. This is a start vertex. So I will add the left edge from this vertex, and its helper will be the first vertex. I have a second start vertex. So I add another left edge with another helper. And then I get to that merge vertex. So here I'm at the end of the orange segment, so I will just remove that segment and I will update the helper for the red segments. Then we get to a regular, and well, by the way, this merge vertex becomes the pending merge for the red segments. So now I have a regular vertex, and since I have a pending merge, I can create a cut. And the new vertex will become the new helper. So I cut here and I update the helper for the red edge. So now I go here, so I will have to remove the red edge and add the next edge on the left. We get to another regular vertex, so I will update the helper. And now we get to a split vertex. So we need to remove that split vertex because it's causing non-monotonicity. So we will cut with the current helper. And we also need to add the new edge for the right-going branch of the polygon. And here, the helper for the blue and the red are the same. Here, I'm at an end a vertex, so I just remove the red segments, but the helper for the blue segments remains the same. And I got to the end of my algorithm. And so I have split my polygon into monotonic pieces that I can then use my previous algorithm to triangulate that one. So let's summarize. We have all division and triangulation that are still done on the CPU, and then you just send triangles to the GPU. We have that trade-off during subdivision with possible pathological cases. The triangulation step itself seems hard to offload to the GPU because it seems to be very sequential in nature, although maybe it's possible. I haven't really explored this possibility. This doesn't really handle holes and complex polygons that self-intersect, and you have to be consistent with the winding. Otherwise, you would have to determine the winding at runtime and do a bunch of unnecessary cross products. And this is scaling in n log n, because although all the algorithm I presented are linear, you have to sort the vertices first. Which leads us to our next method, which is based on triangle fans. So the idea of the triangle fan methods is explained in a very good blog post by Evan Wallace that you can read on Medium. I also wrote a blog post on my website. And the basic idea is that you draw a triangle fan from an arbitrary point to each vertex on your path. And then you use the graphics pipeline to compute the winding numbers of each pixel by counting the number of triangles the pixel is covered by. So let's say a word about winding numbers and fill rules. You have that path of an Orca on the right, and you want to know if a point is inside or outside the path. What you can do is shoot a ray from the point to the infinity on the right, and count the number of times it crosses the path. And you will count +1 when you cross an edge going up, and -1 when you cross an edge going down. And the result of this computation is called a winding number, and it's essentially computing the number of times the path turns around your points. And then you can apply a fill rule to determine if the point is inside or outside the path. And so the even odd rule states that a point is inside the path if its winding number is odd, and the non-zero rule states that a point is inside the path if its winding number is non-null. They do the same for simple shapes. Their behavior is different for shapes with holes or shapes with that are self-intersecting, so you might want to use one or the other depending on the case. You can have a variant of this method, which is like the triangle fan method. The idea is that you draw a triangle fan from an arbitrary point t to each vertex on your path. And then for the point you consider, you just count the number of triangles that cover that point, and you count +1 for a clockwise triangle, -1 for a counterclockwise triangle. And you can see that it's essentially doing the same shooting ray thing, except that each ray is shot in a different direction for each point. This opens the way to a pretty simple and effective GPU implementation where you just upload all your vertices and you make one draw call with a triangle fan primitive. And then you can use the stencil buffer, or if you don't have a stencil, or you can use some kind of blending to compute the winding numbers for you. And at the end, you can draw a quad over your whole shape, and you will reject or accept pixel based on your stencil. So how you do with curved edges? What you can do is that you can do the triangle fan methods for all the curve endpoints that will give you a base polygon, and then you will add triangles for the curves to extend or carve out that polygon. So you have to triangulate the convex hull of the curve control points that will give you one triangle for quadratics and one or two triangles for cubics. But in those triangles, you need to consider only the points that are between the curve and the segments that join the endpoint. So you have to have a kernel or a shader that tells you on which side of the curve a point lies. On which side of the curve the point is on. So enter Loop and Blin, which is this very interesting paper from 2005. What it does is basically it shows how any quadratic or Bezier curve can be mapped onto one of a few canonical curves that we know an implicit equation for. So you have your point in xy coordinates, and you transform that into k, l, and m coordinates into one of those three canonical curve spaces. And then you can tell if the point is on the right or the left of the curve by evaluating an implicit equation, which is k cubed minus l times m. And it so happens that this mapping is linear, so you can pre-compute the KLM coordinates for the vertices of your triangle and let the graphics pipeline do the interpolation for the interior pixels. There are some caveats. So in this method, I didn't do strokes like the last one. I just offset curves, so I create polygons to do the stroking. And then I use the same triangle time method for strokes and fills. Using the stencil buffer or using additive blending is impractical when you have several shapes, because shapes can overlap and you really want to compute a single winding number per shape. And you also have to process shapes in order to do correct blending. And you also want to keep a single draw call. So the stencil buffer is not very practical for that. So instead I used compute shaders that run for each pixel. And I added like a shape index to each triangle. So the compute shader can go through a list of triangles, compute the winding number, and when it sees a new shape index, it knows that it can apply the fill rule, shade the pixel, and go to compute the winding numbers for the next shape. And obviously doing that for every pixel and every triangle is very expensive. So I added a tiling step where I bin triangles into tiles, and then the raster shader is run for each pixel, but it only checks the triangle that are covering the pixel tile. It works like this. I first have a bounding box kernel that computes the triangle bounding box which is used for the binning part. I then have a tiling kernel that bin triangles to tiles. And so each tile has an atomic tile counter that you bump each time you add a new triangle. So, and you have a triangle index arrays. So you have one triangle index array per tile. This triangle index array index into an index buffer that itself index into a vertex buffer. You have to sort triangles after binning, because we bin all triangles in parallel, so you might end up with a triangle of different shapes that are interleaved. So you want to sort triangles by shape ID, and then you have a render kernel where it transforms pixels, it goes through the list of triangle of that tile, it computes coverage, and it does the shading. So here, most of the work is uploaded to the GPU, except the curve offsetting part. It handles holes and self-intersections. It doesn't impose specific winding, and we can avoid all curve subdivision, which means that we create a lot less triangles than linearizing all the path and triangulating all the polygons. It is still very slow. The text example on the left takes 14 milliseconds per frame. The GhostScript Tiger takes roughly 30 milliseconds. And this is due to the fact that you are doing a bunch of redundant work, and you can't really detect occluded shapes and curl them. And there's a bunch of computation that you shouldn't really be doing and that you can't really avoid. And also you have to evaluate the implicit equation for each curve and each pixel. So it's still pretty expensive, which leads us to the third iteration, which is based extensively on tiling. So this is called the lattice clipping method, after a paper from Nehab and Hope that is refined later by Ganassim and colleagues. The basic idea is that you split path into monotonic curve segments, and you bind those monotonic segments to tiles. And then you can compute winning numbers locally per tile. So you compute all your tiles in parallel, and then you have to fix up the winning numbers of the tiles in a later pass. So that's the idea. Let's see how it works. The first step is monotonizing your curves. So you want only curves that go in one direction along each axis, but never curve back or loop or anything. Lines are obviously already monotonic. For a quadratic Bezier, you have to find the splitting point. So each coordinate of the quadratic Bezier is a quadratic function. So if you want to know where it goes back, you have to get the derivative and solve a linear equation. And for cubic Bezier, similarly, we need to solve a couple quadratic equation and linear equation. And we also want to split at double point when you have a loop. You have a double point, and we want to split also at that point. When you have your split points, you can now compute new control points for all the subcurves using Bezier blossoms. And then you have your monotonic curve segments that can be categorized into 4 different groups, depending on the corner of the bounding box towards which the curve bends. So the curve can bend toward the bottom left of the bounding box, or the bottom right, or top left, or top right. And having this categorization means it's easier to tell if a ray is intersecting the curve. So if you have a point and you shoot your ray to the right, if your point is above or below or to the right of the bounding box, you know that the ray won't intersect the curve. And if the point is on the right of the bounding box, you know that the ray will intersect the curve. If you are inside the bounding box, if you are on the left of the diagonal between the endpoints of the curve and the curve is on the right, you know that you will intersect the curve. If you are on the right of the diagonal and the curve is on the left, you know that you won't intersect the curve. And the only case where you have to actually evaluate the implicit curve equation is when your point is on the same side of the diagonal as the curve. So now we get to the meat of the algorithm, which is the lattice clipping part. So the idea is that we want to partition the space into tiles, and we want to process all our tiles independently in parallel. The problem is that computing winning number is not a global problem, is not a local problem, it's a global one. So a segment that is far on the right can still interfere with your winning number. So what we can do, though, is that we can create a set of paths that gives equivalent winning numbers as our input paths. And we do that by adding shortcut segments along the edges of the lattice. And so you see that on the figure on the right. And you can notice that the shortcut path on the left, bottom, or top don't actually interfere with the computation of the winning number. So we actually care only about the green shortcut segments. And here you might say, okay, we knew how to add those shortcut segments because we knew the whole path. But if you look only at the center tile here, for example, you can't say, looking only locally at that tile, whether we should add shortcut segment on the right and whether it should go up or down. However, you can notice that if we have a closed path and it exits the tile from the right edge, it must go back to the tile. So it must either go back from the right edge, or it must first exit the row from the top or from the bottom. So we can create shortcut path from another entering curve segment, or to the top of the row or to the bottom of the row, which is shown on the middle column here. But we can't really decide that locally either, because we don't know if the curve crosses from the top or from the bottom, and it can happen on a tile far away on the right. But what we can do is that we can make a consistent guess and always create shortcuts to the top. And then when we encounter a segment that is exiting the row from the bottom, we know that all the tiles on the left, we made a mistake. So we can create a backdrop. So essentially create a segment that spans the entire tile for all the tiles on the left to correct for the mistake we made. So that gives us a set of local lattice clipping rules. So if you have a segment in a tile, you just update the pixel on the left of that segment. If that segment crosses the right edge of the tile, you have to create a shortcut to the top. So you update the pixel above that segment. And if your segment crosses the bottom of the tile, you know that you have to add a backdrop to all the tiles on the right. So what you do is that you just store the correction that you should make to the tiles on the left, and then you can propagate that correction by doing a prefix sum along the whole row of tiles in a later pass. So the basic implementation looks like this. You first monotonize, then you bin your monotonic segment, then you propagate the backdrops, and then you raster. There are a couple issues. As before, we want to compute separate winning numbers for each shape. We must process shapes in order for correct blending. And that seems to create a lot of overdraw and redundant work. But there are a few key insights that can make this faster. The first one is that although you have to process shapes in order, the order of segments inside shape does not matter. As long as you keep segments of the same shape together, the order in which you evaluate them for updating the winning numbers does not matter. We can also, with this method, detect entirely filled tiles early. These are the tiles that have no segments, but still have a non-zero backdrop. And when you have a tile like that, you know that it's an interior tile, so it's entirely filled. And if the fill color is a solid color, you know that it occludes all the shapes below it, so you don't have to process those shapes. We can also render front to back using pre-multiplied alpha, and that allows us to cull shapes per pixel. When we encounter a pixel that has a solid color, we just stop evaluating the other shapes for that pixel. So the real implementation looks more like that. Our input is the path buffer that contains like the color of the buffer, and like the image, the gradient, whatever. And an element buffer, which is your quadratic and Bezier curves. Our screen is partitioned into 16 by 16 pixel tiles and 16 by 16 tiles chunks. The chunks are not strictly necessary, but it adds another level of partitioning that makes subsequent passes faster. And the part of the pipeline on the left builds a list of tile operation for each tile. So a tile operation can tell you to just fill the whole tile with a color or evaluate the winning numbers with respect to one segment, or to apply the fill rule and shade the pixel. And then you have on the right a raster kernel that is run for each pixel, and that goes through the list of tile ops in the pixel style, and that does the pixel shading. So in a bit more detail, we have a path setup kernel that allocates tile op queues for each path. So for example, you have a path that covers 3 by 5 tiles. So you will allocate 3 times 5 tile queues for this path. And then we have a segment setup kernel that does the monotonization and implicitization of curves, and that binds up segments operation to the tiles queue of its path. And that's where you also mark backdrops and right crossing edges. Then you propagate those backdrops by doing the prefix sum along the rows of tiles. In parallel, we have a chunking kernel that binds entire path into chunks. And then we have a merge kernel that runs for each tile, and it goes through all the path in that tile's chunk and concatenate the tile ops queues for those paths. And that's where we can also detect fully covered tiles and call occluded path and eliminates their tile ops entirely. And then you have the raster shader that runs for each pixel and just interprets the list of ops for each pixel. And at the end, it writes the output to an output texture. So these methods simplify the computation of the winding number. In most cases, you don't have to evaluate the implicit equation. You just have to do a couple of checks whether you're below on the right or the left of the bounding box or the diagonal. Most computation can be done in parallel per tile, so it parallelizes well. And the fix-up stage can be made parallel per row of tiles. There's no need for sorting steps since paths are kept in order during the whole pipeline. And we are able to avoid a bunch of redundant work by calling occluded shape at a tile or pixel level. Obviously, it scales better with lots of shapes that have solid colors because you can avoid a lot of work. If you have a lot of transparent shapes, it doesn't work as well. Performance-wise, it's better, like 2 to 3 times better, but it's still quite slower than I like and that what I think is possible. Raf Lavian, who has done a bunch of very interesting work on vector graphics, has very good figures for a method that looks a lot like what we are doing here. So I'm hopeful that there are parts of the implementation that it can improve. In the work we are doing, there's like approximately 10% that seem to be due to WebGPU overhead. So maybe we are hopeful that WebGPU will get better, or maybe there are ways to massage the commands we send to WebGPU to avoid it to do unnecessary work. But the bulk of the operation, after doing all the binning, etc., is going to the raster kernel, and there are ways to improve things there. There are ways to unify code path between different kinds of curves and to simplify the evaluation of the implicit equations. In terms of future plans for that method, of course, optimization is an important one. I think there are still ways to improve using the same kind of method. Then we could do the stroking on the GPU. So there are methods to offset curves on the GPU that can parallelize well. Haven't tried yet, but that's an avenue for exploration. We can also try to explore analytical anti-aliasing. Currently, there's just a loop in the raster kernel that computes the winding numbers for a bunch of for a bunch of samples for one pixel, and then compute coverage for that pixel based on those samples. So we could maybe eliminate that with a more analytical approach. We could add fast path for commonly used shapes like circles, rounded rects, capsules that are used a lot in UIs, for example. And of course, we can go crazy about effect like adding blurs and shadows and so on. So that's all for future plans. That's all for my journey. So thanks for watching, and I'm happy to take questions if you have some.
Thank you so much for that. That was a wonderful presentation.
Thanks.
Let me see. I got to switch back to a scene where we're both visible. 1 second. So that was fantastic. I've got a few questions of my own that I can use to kick things off. But if anybody has questions for Martin about any of that stuff, then please just drop it in the chat, and Martin will be able to answer. And yeah, actually, let's just go with BYP's question first, because that's as good a place to start as any, just digging back into one of the algorithms that you presented about. So let me jump back to your presentation, and you can sorry to I'll read the question out loud for the benefit of later YouTube recordings and such. Could you go over adding shortcuts and backdrops? They seemed to come out of nowhere.
Over adding shortcuts and backdrops. So for the this slide, I guess. Or yeah, actually, let's go back to that one. So so basically, you want to add only the shortcuts, which are those green ones, because it allows you to compute the winning numbers for the path independently for each tile. But you can't do that. Like, for example, if my path was wound in the other way, in a clockwise way, I would have to add those shortcuts going from top to bottom. But I can't know that by looking only at one tile and not the other ones. So what we're doing is that we are always adding shortcuts to the top of the row. So that's what we are looking at here in the third column. So so you have basically the three cases, which is when you exit from the right of the side, either you re-enter from the same edge, or you go first, you exit the row from the top or from the bottom. And what we want to add is those shortcuts in green, or red. Green meaning you're going up, so it will increase the winning number. Red going down, it will decrease the winning number. So those are the real shortcuts we want to add. But you can't decide that. So what you do is that you always add a shortcut to the top, and when you encounter something that crosses the bottom edge, you know that you made a mistake, and you add a backdrop to all the tiles on the left. So in the first case, that doesn't change anything. We have that segment. Okay, we add shortcuts to the top. We add that segment. We add a shortcut to the top. It's equivalent to the path we had on the left. This one, we have just one segment that is crossing the right edge. We add an edge to the top, and it was actually the right guess, so doesn't change anything compared to the center column. And this one is actually the interesting case, because we make a wrong guess here. We should be creating a shortcut to the bottom of the row, but we are creating a shortcut to the top. And what we do is, when we encounter the part of the path that is actually exiting the row from the bottom, then we had a backdrop. And you see that this backdrop will actually cancel out with the wrong guess we made here. So it's as if we didn't add that wrong guess. And the part that is not cancel out is the real shortcut that we should have made.
So a couple questions from me just related to this. Is it the case that later when you are like performing later parts of this tiled pipeline, like the rasterizing and such,
Yeah.
is this all effectively reducing the problem down to like rendering lots of small shapes? Like are these shortcuts like actual edges that are now being rendered as part of the
So
has the
no.
problem been reduced to a smaller shape, or am I misunderstanding what the purpose of these shortcuts is?
Well, in the abstract, yes. In the abstract, what you are doing is like reducing that big shape into a lot of small shape. But in the implementation, you are not really doing that. If I go to my lattice clipping local rules, so here is like the normal boring case. You just update the winning numbers on the left of the segment. Here is where you add segment to the top. So you don't actually add a segment like an input segment and treat that. You know that you should add a shortcut segment. So you know that you just have to update the winning numbers of all this band here and to add 1 to all those winning numbers. But you don't actually add a segment, right? Same thing here, because like your segment that is crossing the right edge is going down. So you know that you have to update all that band with, that should be a -1, by the way. I just messed up the diagram.
Red plus ones.
Yeah. So yeah, red are -1s. And so now for that, you don't actually create backdrop segments for all the tiles on the red. You just saw that you made a mistake and should propagate the correction to all the tiles on the right. So you are not actually adding input segments.
And it's just part of the winding number calculation that is performed on that tile later by making assumptions about, or not by making assumptions, but by sort of reasoning about the way that the shape can move outside of that specific tile.
Yeah. Basically, when you are computing the winding numbers, you only do that like locally, and then you have a step that does the correction that you basically offset the winding numbers of all the pixel in that tile by the value of the backdrop.
And if there are no other questions from chat, then I will go ahead with another one of my questions related to this whole process, which is, could you go over again how you can then tell whether a given tile, and if you go to the previous slide, I think, the one with the circle, or I guess this one, yes. How, again, can you tell when you're later on whether one of these tiles, like that center one with no edges crossing it, is inside or outside?
Yeah, so this one I might have prepared a slide just for this. Okay, so here we have an interior tile, and it is just handled the same way. So when you look at that tile locally, you just don't do anything because you don't have any segments. But then when you see on the right tile that you have a segment crossing the bottom edge, you know that you made a mistake, and you add backdrop here, and you should add a backdrop there also. That figure is incomplete. But basically, it is handled by the same set of rules, and the backdrop will always correct even for interior tiles. So you can have interior tiles that have no segments, but that have a backdrop. And that's how you detect that they are, in fact, interior tiles, and that you can fill them entirely and maybe cull the occluded shapes behind.
What's the origin of the term backdrop? Shortcut, I think, makes a little more like intuitive sense to me, in that it's like we're sort of pretending that the path took this quick, instead of whatever it ended up doing, we're pretending that it just jumped straight up. But the backdrop bit, I'm not sure I really understand.
I don't really know for sure. I think that is just meaning that you have um, like behind all your shortcuts, you had like a shortcut that spans the whole tile, because backdrop updates the winding numbers for all the pixels in the tile. So that's like your that's like a winding number offset, if you will. And I think the backdrop kind of thing comes from there. That's the background value of the winding offsets, if you will.
I see. That makes sense. Going back to the triangulation approach. So, as I understand it, this was the first approach that you tried for your own. Was it just the first one for Orca, or the first one for vector graphics rendering in general?
This was the first one for vector graphics. The first one for Orca was the triangle fan.
Oh, okay.
And then I've moved to the Niab and Hope method, like the lattice clipping.
One thing,
but the triangulation was before that. Yeah.
One thing I was curious about for the triangulation approach was, does that approach have sort of resolution issues for curved path segments? Because you described like sort of sampling a Bezier at different points and generating triangles. So would it be the case that that technique would actually produce sort of corners along edges that were supposed to be smooth curves, or am I misunderstanding?
Yeah. So yeah, basically you piecewise linearize your curves. So it depends on how fine you want to go. So what you would do, for example, when you are splitting your curves and checking if the point on the curve is close enough to the segments between the endpoints, if you make sure that you're always that this distance is always less than 1 pixel, say, you will not really see a difference, but that could be very costly. So you're always like doing a trade-off, and the number of time you allow your algorithm to recurse like gives you how much it will be, like how precise it will be. But it also depends on the curve, because for a simple curve you won't have to recurse much, and for a very twisty curve you will have to recurse a bunch of times. But so if you don't want to be too costly, you could be choosing a threshold that means that for some curves you will see some corners. Yeah.
Is the recursion to handle the fact that Bezier curves can't be like sampled at even intervals? Is the idea that you just sort of, you're almost binary searching it to get an acceptable resolution or something, depending on how like tight or twisty that part of the curve is?
Yeah, so the first thing is it's pretty easy to just split Bezier curves and compute new control points for subcurves, and so the smaller your curve is, the more chances you have that it's close to a line. So basically you're kind of adapting your step, because you could just like divide the parameter of the Bezier curves from 0 to 1 into a number of small steps and just linearize that. But you don't know up front if that subdivision would be enough to not make corners. So subdividing like that adapts the resolution of your step to the curvature of your curve.
I see. Interesting. One other small thing being that I had a question about was that at the end you mentioned that there was no need for sorting with the lattice clipping method. I think I lost track of what was being sorted.
Yeah.
Was that because you I believe you said that paths did not need to be sorted. Does that, or was it segments or something else? I'm sorry to make you flip all the way through the entirety of your presentation again. I didn't mean to do that.
So in the triangle fan method, you have a sorting step, because you bin triangles into tiles, but you do all that in parallel. So you end up with tiles with a list of triangles for each tile, but that list of triangle has all kind of triangles from different shapes that are interleaved. So you can't like compute the winding numbers for by just going through that list. You have to first sort that list so that triangles belonging to the same shapes are grouped together, and that shapes are in order you want to evaluate them. So in that situation, you have to have a sorting kernel, whereas in the tiling method I use here, since you do first the path setup and then you bin but path per path, and then you just concatenate the lists for each path.
Okay.
You don't like the paths are already sorted. Like the segments might be unsorted, but we don't care. But the paths are kept sorted. And by the way, that could be also like the same method could be used for the triangle fan method. I just didn't use that because that was way before.
Sure. Because the order, yeah, I mean, the shapes do have some kind of implicit, well, not an implicit order. The shapes have some kind of order that they are supposed to be drawn in for something complex like the Ghost Script Tiger or what have you. Obviously,
Yeah.
there's shapes drawn in the back and shapes drawn in the front. And so the question, I guess, is just how the algorithm, if the algorithm preserves that order or if it needs to go through an additional sort again.
Yeah,
Cool.
exactly.
One, I think we'll wrap up with one more, unless there's other questions from the chat, and please, speak up if anybody has any questions. I want to just segue to Orca a little bit and just ask what your overall goals are for the performance of this vector graphics renderer within Orca. Obviously, you still see that there's there's still room to improve. There's still ways that you can make it faster. I'm curious what your goals are, what kinds of things you would like the renderer to be able to achieve.
Well, so if I base that on the numbers from Ralph Livian, we could go much lower than that. Like a few, like 1 or 2 milliseconds for the Ghost Script Tiger would be achievable. So yeah, that's kind of the targets. The goal, like the thing is, this 2D vector graphics is mainly there to allow drawing UI. So that's not as intensive as doing like complex curves and strokes and stuff like that. It's mainly simple paths. So it's already kind of sufficient right now to draw simple UIs, but I want it to be as performant as possible to just leave the most of the resources to what the user wants to do.
Right.
Besides just rendering the UI,
Yeah, I mean, obviously nobody really wants that to be a bottleneck, which unfortunately is often the case when you try to do more interesting types of UIs on the web, for example. I will say though, I mean, I think that having a very fast vector graphics renderer is exciting for a number of reasons. I was just seeing some conversation at work about the sad state of SVG and poor support of SVG in different places and people wanting to use it but being frustrated because it's too slow to actually do interesting things if you want SVG kind of in your application loop. So I think there's actually quite a lot of interesting application opportunities that open up if you have a sufficiently fast vector graphics renderer. And so it's really exciting to see something like, even the Ghost Script Tiger is non-trivial, certainly, and that's already happening at frame rates that are in many ways better than what we're seeing in other systems.
Yeah, there are other, like for example, if you try to render maps and try like for a map application, you would want to render the map as vector graphics and be able to pan and zoom and do all kind of transformation very quickly. And that can be even more complex, like a full map with all the details can be a lot more complex than the Tiger. So that's kind of the kind of target benchmark I would like to achieve good performance with.
Yeah.
And if we can render big maps at an acceptable frame rate, that would be like a good target. Yeah.
Yeah, I think I remember even a map application being one of the things on our list of
Yeah.
like sample Orca apps from years ago when we were discussing it in Seattle. So yeah, that would be really, really cool to see. Well, I don't think I have any other questions. I don't see any other questions from chat, and we're over an hour now, so I will kick back to just our conversational view here for a second. Thank you so much for being here. I want to thank you again for doing this on quite short notice.
Thanks for having me.
We had a schedule conflict in May that meant that our the speaker that we initially planned on wasn't able to make it. But this is fantastic. Before I do my plugs, actually, I'll do my plugs and then you can do yours. How's that sound? So
cool.
We have some events coming up within the handmade community. There's two major categories to be aware of. First of all, and let me find my scene here. First of all, we have two jams coming up within the handmade community this year. We are doing the Visibility Jam again. That will be July 19th through 21st, a weekend jam. And we will also be doing the Wheel Reinvention Jam again for what I believe is the 4th year running. And I'm very, very pleased to be running that one again. And for those unfamiliar, Martin started Orca as a Wheel Reinvention Jam project. And that has, turned now into a substantial project and one that he works on nearly full time. And it's really, really fantastic to see. So I hope you all join us for that. If you are interested, please visit handmade.network/jam. I am posting the link in the chat. You can sign up for our email newsletter so that you'll make sure to be aware of all of that and other announcements that come out. The other thing to be aware of is the Handmade Cities conferences, Handmade Boston and Handmade Seattle, both happening again this year. So if you are interested in going to conferences and seeing more content like what you saw here today, then please consider buying tickets to Handmade Cities. There are both online and in-person tickets available, and more details can be found on the website, so I'll post that link in chat as well. And finally, Martin, where would you like people to follow you, or what would you like them to look into further if they're interested in what they saw here today?
Yeah, so you can go to my personal website where I have a number of blog posts. So that's forkingpaths.dev. I've shown that in the slide a number of times. There is also the Orca websites, orca-app.dev, where you can see all the updates about Orca, and there might be some updates soon. So you can check that there, and you can subscribe to the newsletter on the Orca websites to keep in touch with the project. You can also sponsor us on GitHub if you want, and yeah. And you can also contact me on Discord. I'm happy to answer questions, have chats about vector graphics, Orca, or really anything programming related. So yeah, that's my my plugs.
All right, thank you. Thank you so much. Thanks everyone for being here in chat.
Thank you very much.
And I will see you all next time for our next episode of Unwind coming later in June. So see y'all later. Bye.